First of all, thank you for inviting me. I am presenting this work also on behalf of my colleague Franco Miglietta. And the topic of the focus of this presentation is on biochar and on how this strategy may impact on land surface albedo. In the last years, there has been an increasing research effort around biochar that is considered one of the most effective negative emission technologies, able to offset a significant share of anthropogenic greenhouse gas emissions. Just to give you an idea of how much is there is an increasing interest in this technology, if you search for the topic biochar in Web of Science, in 2006 you had only 3 papers. Now in 2020, about 15,000 papers, 3,000 of which only in the last years. A large interest around biochar is related to its potential in mitigating climate changes due to carbon sequestration. But nevertheless, its impact on land surface albedo should be carefully quantified. I will give you a short introduction on this topic for those who are not expert on that. In general, if you burn a biomass in the presence of oxygen, you have a process that is commonly known as combustion, and you have the formation of oxidized compounds and the release of heat. But instead, if this heat happens in oxygen-limited conditions or in the absence of oxygen, you have another process that is named pyrolysis or pyro-gasification. And this process yields 3 main products that are a syngas or synthesis gas, mainly composed by carbon monoxide, hydrogen, and methane. A liquid residue called tar that is formed by high molecular weight hydrocarbons, and the solid carbonaceous residues called char that contains up to 90% of the carbon of the original matrix, commonly between 15 and 85%. Well, of course, this residue, the char, can be burned to obtain energy. But if you incorporate this residue into soil, you have an increase of soil carbon stock in a stable manner, because biochar is a very recalcitrant matter. So we can say that biochar is not exactly a material, but it's rather a strategy that can be used to increase carbon sequestration and also has agronomic and environmental purposes. And much of the value of biochar for carbon sequestration is due to its recalcitrance in soils. While biomass tends to be rapidly degraded, consider that roughly 80% of the biomass incorporated in soil are lost within the first year due to the processes of mineralization by microorganisms. Well, biochar is instead very recalcitrant, and we can say that the mean residence time of biochar in soils has been calculated to be of the order of magnitude between 100 and 1,000 of years. This, of course, makes clear why it is so interesting for carbon sequestration. And this is, of course, a very simple representation of what happens to the carbon cycle when I include the biochar practice. Simply, I remove carbon from a small-term cycle and introduce it into a long-term cycle. Another issue is to understand how much biochar is important for yield. Well, in this meta-analysis that is presented in this graph that pulls together a number of different experiments of biochar, we can see that the mean change in productivity is around 10% across different types of soils, of biochar types, of crop types. And what you see represented in this graph aside each bar, it's the biochar application rates in tons per hectare. So there is a clear dependency of increase in change productivity related to biochar application rate. I am not going in depth in the processes by which biochar increases soil fertility, because this is not the focus of this talk. But anyway, the important aspect is that the introduction of biochar in soil induce a change in the physical and chemical properties of the soil, creating therefore a favorable environment for the microbial soil community. And these two aspects together tends to increase the availability of elements of nitrogen on phosphorus, and in general improves the water-plant soil relationships. So biochar is a highly porous media, and introduce it in the soil, you increase the soil water capacity. And estimates have been made on the mitigation potential of a global scale biochar deployment. The most comprehensive is probably this one made by Wolf and co-authors, and is summarized in these schemes that shows the inputs, the process, the outputs, the application, and the impacts on the global climate. The results of these estimates are that in a global application scenario that was defined as a maximum sustainable technical potential, that is a scenario in which food security, habitat, and soil conservation are not endangered. Well, in this scenario, we could be able to offset up to 12% of anthropogenic emissions, with positive feedbacks on the enhancement of primary productivity. Well, so far the good news, but, and of course there is always a but, there are a number of potential drawbacks associated to the use of biochar that should be carefully considered, and also should serve to better define guidelines for its application and agronomic practices. Overall, I have to stress on the fact that the modifications induced by biochar in soil are not temporary, or are not so temporary. This is due mainly to its high stability. And it's this no temporary character is true for chemical and physical changes that influence, for example, soil retention and pH, and all those are positive effects. But it's also true for negative effect, and in particular one that is at the core of this talk, and is that biochar is unavoidably black, and the changes induced in soil albedo are not so temporary as one would expect. As we will see, this may have a non-negligible impact on the mitigation potential of this strategy, together with another drawback, that is the potential release of black carbon aerosols. So far, several studies tackled this problem to better assess the impact of changes in surface albedo at different scales, and to assess also the potential impact of black carbon aerosol release. Several studies, as I told, were made at different scales, from the plot scale to a larger landscape scale. With landscape, I mean from tens to hundreds of kilometers, and at regional scale by modeling to test different kinds of applications, so a surface application and incorporation, and to assess the impact on the short term, on the long term, of different biochar application rates on soil temperature, on radiative forcing, and on mitigation potential. I will start describing this experiment made at a plot scale where biochar was applied at a rate of 30 and 60 tons per hectare on a winter wheat crop in central Italy. In this experiment, we observed an overall albedo change during the year of about 40%, and an anomaly in surface temperature with a seasonal mode. We can see here is represented the changes in soil temperature measured at 5 centimeters depth. And we see that from the brown area that we have an increase in temperature in the after sowing. We have a decrease in temperature when the crop is fully developed because of the higher biomass production, and again after tillage we have again higher temperature in treated plots. So we can say that there is a seasonal mode in the anomaly in surface temperature. There is an increased evapotranspiration, and in general a change in the partition of energy. All these facts, of course, had implications such an accelerated germination of wheat, but also the reduction of mitigation benefit of biochar. When we move to the landscape scale, other elements enter into play and are the fragmentation of land use and the impact of the choices made by the farmers in terms of crop management and crop choice. And we will see that those aspects really matter. As it was not possible to test such a large biochar application, in this study made by Bozzi and co-authors, different sites having different soil albedo were considered in order to simulate on a time series the impact of biochar application. Here we are in central Italy, I would say in a Mediterranean environment. And in particular, 3 pairs of agricultural sites were selected, and within each pair there was a light colored soil and a dark colored soil. So the dry bare soil albedo for each of the 6 sites have been measured in situ by means of spectroradiometer, and to each pair, we associated an estimate of biochar application rate on the basis of a mixing experiment made in laboratory, aiming at the assessment of the dose response curve. So how much biochar should be added to the bright site to obtain the same albedo of the dark site. Then starting from this, in those areas, 12 years time series of MODIS satellite images were analyzed to derive the annual profiles of NDVI, white sky albedo, instantaneous radiative forcing, and mitigation potential reduction. Here I show you just as an example a function of the soil albedo change in the higher left graph induced by biochar application that was derived by the mixing experiment. In the lower graph are depicted the albedo measured for the bright site and for the dark site of each area in dry and wet conditions. And are also represented the amount of biochar that was applied, that was necessary to apply in the mixing experiment to each soil to obtain from the bright site the same color of the dark side. So the biochar application rates were for the first site 34 tons per hectare, for the second site 112 tons per hectare, and for the third site 36 tons per hectare. And this figure illustrates the results of the MODIS satellite time series analysis over 12 years, showing that the median yearly values of NDVI in the upper panels and albedo in the lower panels, where in the lower panels the solid line represents the albedo of the bright soil, while the dashed line represents the albedo of the dark soil. And here it is interesting to observe that the albedo differences are not so strictly linked to NDVI. And hence I would say probably also not so strictly linked to fractional vegetation cover, as albedo result to be different also at high NDVI level, and albedo was always lower in the dark site in 2 out of the 3 sites selected. The only difference we observed was in site 1. I will show later about the particularity of this site, that it was due to the choice of crop. The results of this experiment on the fragmented landscape are that, first of all, soil background has an impact on surface radiation balance, also in high canopy cover conditions. And mitigation potential reduction is lower at high biochar doses, so there is a sort of saturation effect in albedo change. And also that crop choice has a substantial impact on the absorbed shortwave radiation and hence on radiative forcing as well. We can see in the graph in the upper right where the cumulated absorbed solar energy difference is reported between the bright and the dark side, that in 2 of the sites the cumulated absorbed solar energy difference tends to increase over the 12 years, while in 1 of the sites where sunflower was cultivated in 9 out of 12 years, the cumulated absorbed solar radiation is much lower. Overall, so we can say that crop choice has a substantial impact on the radiative forcing, and overall the mitigation potential reduction was estimated to be as high as 12.8%, and this data is similar to other estimates made in other studies that are reported in the table below. An important further step that is required is the regional modeling of such a practice. Especially if we consider that the strategy is not expected only to affect albedo, but may substantially alter the surface energy partitioning. And a first preliminary attempt was made recently by using a regional scale climate model. And the results that concentrated mainly on temperature by perturbing the arable land albedo scheme in a WRF model for 1 year provide the result of a significant impact on surface temperature of about 0.2 degrees in Eastern Europe. But there are further questions that need to be tackled. First of all, there is more need to address by simulation the potential of biochar application. This is related to the possibility to explore its impact on the long term, simulating a process of large-scale application of biochar, of progressive large-scale application of biochar over Europe. And furthermore, other aspects that needs to be better explored are the reciprocal feedbacks between the surface fluxes partitioning and the presence of biochar, better accounting for the enhanced soil water retention capacity and the increase in crop yields. Why it's so important to move toward a regional modeling of this aspect? Because many recommendations can be the outcome of such an exercise. So we can derive recommendation on amendment strategies. So which are the best rates, which are the best procedures. So is it better to apply it in a single dose or multiple doses? Is it better to incorporate or to have a surface application? And also to recommend which are the locations across Europe where the feedbacks on climate can be higher. We have seen before that how much the soil color changes across Europe. So in general, it should be recommended to put biochar where soils are already dark, and is less recommended for bright soils. And a further recommendation that can be derived from modeling experiment is the possibility of mixing the biochar application strategies with other land regional management schemes. And the question that remains about albedo that needs to be further explored is about its permanency. Here we see in the upper picture the image of two soils of a vineyard treated with biochar 5 years after application, and we see that even 5 years after application, the color of the treated plots are much lower. So the albedo is much lower. So different strategies have been proposed also for mixing biochar with other substances. And this is something that should be further explored to see if it's possible to decrease the impact of biochar on soil color. In this picture below, you see an example of mixing of biochar with kaolin, that is another substance that may be used in agriculture. And just as an example about the permanency, I can report some images of an experiment we made on a vineyard in central Italy, where we applied 2 doses of biochar at 4 tons per hectare and 20 tons per hectare in 2009. And we see that in 2010, the difference in color, of course, this is an aerial picture, so it cannot be considered an albedo measurement. but anyway provides an idea of the changes in color of soils. And in 2010, the treatments are still clearly visible, and also are clearly visible in 2013, so 4 years after the biochar application, and still perceivable in 2016 and slightly perceivable in 2019. So at least 10 years after biochar application, I still may have an impact on albedo. And finally, here we come to another issue that have to do with biochar application, that is the release of black carbon aerosols. We know that the irradiance, that is the amount of shortwave radiation that reaches the Earth, is modulated by the burden of aerosols. And we also know that light scattering and light absorbing aerosols have opposite impact on the radiative forcing. Light scattering aerosol reduces radiative forcing, while light absorbing aerosol increase the radiative forcing. As the short wave they absorb is later re-emitted as a long wave. Well, when biochar is produced, but also during the transport, the application, and during the tillage, it is unavoidably crushed into small particles that can be released in the atmosphere. In particular, the smallest particles belongs to the category of black carbon aerosols that are defined of particles with a diameter smaller than 2.5 micrometers, and that are refractory, water insoluble, and strongly absorb light, visible light at a length of 550 nanometers. So, of course, this is a fact that should be considered while applying biochar. And we can say that black carbon aerosols may impact the radiative balance in a non-negligible way in two directions. First of all, through the direct modification of shortwave absorbance of the atmosphere. And secondly, indirectly, after its deposition through a modification of surface albedo. To this end, in particular, it's important to remind the potential impact it can have on snow melting, as we know that from these synthesis studies, for example, 20% of the total glacier melting is due to the deposition of black carbon aerosols. And finally, I come to the conclusions. The first conclusion is that biochar is very effective for climate change mitigation, and it is a strategy that is able to conjugate the mitigation with adaptation and with increased productivity. And another important fact is that biochar is also easily to be quantified as a mitigation strategy. The second fact is that biochar unavoidably modifies soil albedo, and this change is not so temporary. So it may modify soil albedo on the long term. The third fact is that biochar application may increase the release of black carbon aerosol, and to this end, specific practices should be designed to reduce this release. Which are the recommendations? First of all, biochar should be applied together with other land radiation management schemes, such as cover crops or residues management, as we have seen before, to minimize its impact on albedo changes. Secondly, we have to optimize the agronomic practices and choose also the appropriate locations. So, okay in dark soils, I would suggest no in bright soils. And finally, we have to avoid the biochar release during the production and application. And in this respect, for example, a specific soil water content of commercial biochar have been prescribed for commercial purposes in Italian legislation about biochar. So I have concluded. Thank you for your attention.